All right, guys. Seriously, if this doesn't work, I'm coming to your house with my overhead. I am doing that. So cross your fingers and show up at your house. Anyway, where did we start? We started with organic chemistry, watching how carbon, or learning how carbon bonds to itself, makes all kinds of different crazy shapes and everything. We learned about alkanes, alkenes, alkynes, and how to look at the general formula to see which one you like, which category it fits in there. See if you have saturated, single bonds are saturated. If you have doubles or triples, right? Alkenes or alkynes. And then we learned about naming branched hydrocarbons. So that's like when you got boop, 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 with like little, little things sticking off all over the place. And then we like messed it all up with like functional groups. That's where like you take off a hydrogen and you add on an oxygen. It could be an OH, a hydroxyl group. It could be a double bonded oxygen. Is the double bonded oxygen on the end? Or is it in the middle? Because that totally changes the way it works. What if you had a double bonded oxygen with a hydroxyl group? And then you got yourself an organic acid. I know, it's crazy. And what happens if you have like an oxygen just in the middle? Like if two primary alcohols come together, boop, what you get? You get, an ether, because like two H's and an O boop off, and there you got your double bonded, or your single bonded O in the middle of your hydrocarbons. Then you got the esters with like, oh, it's just craziness, isn't it? And so, and then the amines, and then the amides. It's a lot to keep track of. That's why we use the reference table. All you got to do for those is look at the reference table. And now what we're going to do, these are not, unfortunately, are not in the reference table. So what I need you to do with these is you got to lock the words in your brain. That's really the whole point of this. There's words, you got to know what the words mean, and then you got to be able to recognize. Okay? So that's how we're going to do. First one we're going to do, combustion. You guys should know what combustion is. Dear God, I hope by now you know what combustion is. It's when stuff combines with oxygen. And for us, specifically in this chapter, it's when a hydrocarbon bonds with oxygen. And when you do that, you end up with, let me turn this on, carbon dioxide and water, right? Anytime a hydrocarbon burns, any kind of hydrocarbon at all, or any carbon-based anything, you are going to get carbon dioxide and water. Here's what you need to do. Recognize, define, and balance. Oh, everybody loves balancing, so let's just dig into it. So we know that this is going to be a combustion reaction because we have a hydrocarbon combining with oxygen. Like that's it. An organic molecule reacts with oxygen. All right. So all we have to do is count. So remember, and so we have our coefficients, and if there's nothing there, we assume it's a 1, times our subscripts, and that tells us how many. So 1 times 4 is 4. 1 times 1 is 1. 4 and 1 are not the same, so we're going to go like that. 1 times 4, 4 times 1. Excellent. Now we're going to go to hydrogen. Remember, if hydrogen is difficult, skip it for the end. Like, it doesn't have to happen right away, but let's just see what happens. Here I have 8, right? Because 1 times 8 is 8. Here I have 1 times 2. Nope. Okay, 4 times 2. There's 8. So 1 times 4 is 4. 4 times 1 is 4. 1 times 8. 4 times 2 is 8. Now for oxygen, I have 2. 1 times 2. 4 times 2, well, that's 8 for oxygen, and 4 times 1. So I have 12 in all. So what times 2 gives me 12? 6. Boom! Balanced chemical equation. Don't even act like you're scared of that because I know you can do it. Next one, substitution. Look, this is one of those situations where we are not trying to be difficult with the name. Y'all know what substitution is in a sport, right? One player out, one player in. That's the way it is with a chemical reaction. It is where a hydrogen from a saturated thing is replaced. That is what's clutch here. Substitution is replacing something. So here's what a substitution chemical reaction looks like. Here is my organic hydrocarbon. And if you noticed in the beginning, compared to the end, right, we're going to want to look and we're going to want to compare. Over here, we've got nothing but hydrogens, but over here, do you see how we have substituted or switched out a hydrogen for a chlorine, right? Well, where did that hydrogen go? Oh, there it is. There, not too far away, right? You guys get, do you see how like one thing is going in and another thing is going out? So for a substitution, you got to pop out a hydrogen so you can smoosh in something else. Do you guys follow? Well, that was just one. You can also do this. You can take it to like the second. So the product here, we're going to make a reactant, and we're going to take these two things and react them. And look what happens in my final product here. So remember, we're comparing and contrasting. 5 hydrogens. Here we only have 4 hydrogens. So 1 hydrogen has come out. 1 chlorine, 2 chlorines. Oh my gosh. It looks like 1 hydrogen went out, 1 chlorine went in. That sounds like substitution, where you take one thing out and put another thing in. Right? I mean, literally, just like a substitute for like football or something. You guys dig what I'm saying? Super! That's pretty easy. The next one is addition. Here's the thing. Single bonds do substitution. Single bond substitution. Single bond substitution. When you do addition, you will have a double or a triple bond because you are literally smooshing the two things together. So let's take a look there. Here we have a double bonded, or 2 double bonded carbons, and here we have a halogen. The way that we know it is addition is 1. Do you see that right there? See that double bond? It's gonna have to be addition. And also over here in our product side, you see how we have added them together, right? It is this plus this makes this. Bam, done. Dig? I mean, that's what addition is. You're adding 2 things together. That's it. The clutch thing here, like the thing that'll make it easy, is that double bond. Anytime you see a double bond, it has to be addition. Also, if you look at the chemical reaction, if you look at this, first you start with 2 things, and then you are ending with 1 thing. You are literally adding them together. Got it? Great! Moving right along before my computer crashes again. Esterification. It's like right there in the name, guys. Esterification is quite literally making esters. A couple things you're going to need to know about this. One, I need you to know what the word esterification is, and we need to know or remember that an ester comes from an acid and an alcohol. Okay, and here's a little like reminder of how it happens. This is like what's going on inside like a barrel of wine as it's like sitting and waiting and like maturing, so you get all these like crazy flavors. And this is also, not for nothing, how they make flavors for like dum-dum like lollipops and things like that, artificial flavors. This is one small category of artificial flavors. Where you take this is your organic acid, and this is an alcohol. Right? And what happens is, right, if this H and OH, right, 2 hydrogens and 1 water, right, this is going to pop off. Bloop, and look, there it is. You will make a water. Why? Because water is like the most crazy stable thing in the world, and that's just sort of what happens. And so what's happened is this carbon has an open bond, this oxygen has an open bond, and so they're going to reach out and bond to each other here, right? So as soon as that water pops out, the carbon and the hydrogen, they like form a bond, and here you have your ester functional group right now. Now here's what I want you to see. Is over here, do you see how this carbon right here has this double bond? Well, there it is right here. Here's the carbon, and there's the double bond. Well, the double bonded oxygen to be clear, right? So when you look at this ester, this portion came from the acid, and this portion came from the alcohol. Now, how can you tell that? Well, because an acid has a double bonded oxygen and an alcohol does not. So therefore, the side of the ester that has the double bond, which is also where we get the root name from, if you remember, it also comes from the acid. And this side, because there is no double bonded oxygen, it comes from the alcohol, because alcohols don't have double bonded oxygens. So how does that apply to us? Let's come down here to this mess of a thing. And I want to ask you, you will be asked questions like, well, what acid and what alcohol could have made this crazy looking ester thing right here? Well, the first thing we're going to do is we're going to look at it and be like, okay, oh, here's my double bonded oxygen. Remember, esters, we're going to split it. We're going to divide it down that oxygen, right? And so here I have my double bonded oxygen. So the alcohol and the acid and the alcohol, we can see which one is which, because this guy right here, this double bonded oxygen that you guys are looking at, remember that's from the acid, right? So it must be a 1, 2, 3 carbon acid. So it'll be 1, 2, 3 carbon acid. right? Because the double bonded oxygen comes from the acid. Now over here, this is going to be our alcohol. So how many carbons are in this one? We got 1, 2, 3, 4, 5. So this will be a 5-carbon alcohol. So I'm going to draw the hydroxyl group here. There. That's the alcohol. Meth, eth, prop, propanoic acid. Meth, eth, prop, but. Pentanol. Sweet, easy, done, right? Again, when you have your ester, you're going to split it down the oxygen. The side with the double bonded oxygen, that came from the acid, and the side without the double bonded oxygen, your alkyl group, your branch, that came from the alcohol. Lovely. Moving on. Soponification. Saponification. I like to say soponification. It is the process by which we make soap. So here's the deal. We're going to take an ester. Typically, this is a fat from some source. In the old days, they would take lard, right? They would take fat, they would cook it down like basically the bacon grease that's like at the end of cooking it. You pour it into a container, you add a base, and when you're done, you end up with this triol, or this alcohol, and soap. So let's dig into it. What you need to know is a few things. You need to know, first, the definition of saponification, right? So you need to know that definition. You also need to know that this is called glycerin, or triol. Oh, that should be an H. There, I'm going to fix that right there. Or a triol. Because look, all fats, it doesn't matter if it's an animal fat, if it's palm oil, if it's olive oil, any kind of like fat, right, that comes from a living thing, is basically a triglyceride, or right. So what you have here is this R is a hydrocarbon, and a hydrocarbon, and a hydrocarbon. And the thing that makes this like olive oil is which 3 hydrocarbons you have. The only difference between like olive oil and like coconut oil or peanut oil are what these 3 things look like. Also, whether it's like bacon fat or like beef tallow or whatever, it just depends on what these 3 R groups are. Human fat is very much the same thing. We have this sort of staple part here and 3 different hydrocarbons. That's what a fat is. So what happens is when we add a base to this, the base basically cuts it right here. Cuts it right off, right? And we are left with this guy, which is called glycerin, or a triol, because it has 1, 2, 3 hydroxyl groups. Glycerin, really common. It's they put it in like chewy granola bars or chewy chips, or chewy chocolate chip cookies. It's one of the main ingredients to like children's Tylenol, because it's a syrup. It's really sweet. It's clear. It's kind of like tasty. And what we are left with are 3 of these things. Here is how soap works. This R group, this is a hydrocarbon, and it is very non-polar, right? This side over here, as you can see, is ionic. So when we take a soap molecule and we put it on our hands, the reason why you have to go like this for like, I don't know, how long is it until you sing happy birthday, is because as you're physically rubbing it together like this and getting in between your fingers and rubbing your thumb and taking your fingernails and putting it in your palm and going like that to scrub underneath your fingernails and your cuticles and the palms of your hands and the nooks and crannies of your fingers. There's a whole technique you should be watching your hands. What you're doing is you're working this part. This non-polar hydrocarbon is going to wiggle into all the little dirt and crevices, like little nooks and crannies of like every little like part of your hand, and it's going to basically attach to all of the non-polar grease and grime, right? And then this side here is going to attach to the water. And so as you're going like this, you're forming these little teeny cell-like structures where it kind of bubbles around the dirt. And when you rinse it with water, this ionic part, this part attaches to the water, and the water physically like brushes it off of your hand. So what it does is, again, it captures all the nonpolar grit, and then this part has a polar outside so the water can grab it and take it off of your hands, and everything goes away. almost. So that's how soap works. What you need to know really well is the definition of saponification. You also need to know the structure of glycerin, like the byproduct of making soap. And it's also just good to know how soap actually works. Again, the nonpolar part sort of bubbles around all the dirt in your hand, and the polar end of the soap attaches to the water. So as you rinse your hands under the running water, the water is physically grabbing onto those little bubbles and pulling it off of your hand, and away with it goes all of the dirt and grime. Lovely. Who knew that that could be such a way to avoid infection? But it is. All right, next one, fermentation. This is where yeast breaks down sugar into alcohol and carbon dioxide. You just need to be able to look at this and recognize it. How are you possibly supposed to recognize this? Well, I know from the cracks that you all know what C6H12O6 is. You know what that is. And this, now that we're all smart, we know that this is an alcohol, and we know that this is carbon dioxide. You dig? Great. I mean, that's how they make champagne and stuff. That's how they make beer bubbly. First, you do what's called the primary fermentation, where you like basically make it gets all alcoholic, and then you pop in just a little bit of sugar and put the cork on it, or put the beer cap on it. What happens is you have to do it just right, like just the right amount. And as it ferments, it makes carbon dioxide, and carbon dioxide dissolves in water. And then some doesn't, goes into the teeny little airspace above, and then it causes a lot of pressure because it keeps making carbon dioxide. And what does an increase in pressure do for the solubility of a gas? It increases it. So that's how it dissolves the carbon dioxide in the water. Pop the top off, lower the pressure, gets all bubbly. You need to be able to recognize this. Can you handle fermentation? Thought you could. Moving right along. Polymerization. On this one, this is where we're going to get a little bit tricky here. All right. So polymerization is where we make really, really long chains of molecules, and these are made up of monomers. Mono meaning one, mer meaning units, right? So a polymer, right? Many units. This is where we take a bunch of the same things and we link them together, okay? And there's like two basic ways that we are going to look at. One is addition polymerization. So this is where we take our monomers and we link them through an addition polymerization. It's an addition reaction. And here's basically how it works, right? So we're going to take something like this. This is like vinyl chloride, and N, whatever number you want it to be. Okay, so let's make a really teeny one. Let's make 37. We take 37 of these monomers, right? And with the help of a catalyst, we can make these things link to each other by breaking this double bond. Does that make sense? And so our polymer, like the notation that we have, that we use to make sure that we know that we're talking about a polymer, is first we write down what the monomer is, and we put it inside of a bracket. So you see this bracket here? This indicates that that is one bit or one monomer of our polymer. And then these bonds, if you notice, are sticking outside of that bracket. And that outside bond is sort of trying to show that these are all linked together. And then N, in this case, if we started with 37 monomers, this has a subscript of 37 to indicate that this polymer is made up of 37 monomers. Now, in reality, this is going to be a huge number. For example, this is called polyvinyl chloride, or PVC. Like the plastic plumbing, right? Like there's white plastic tubes. So that's all one molecule. If you ever see those big giant black plastic tubes on the back of a semi truck going down the highway for I don't know, sewer or whatever, dude, that's all one molecule. So when they make this, they take all the monomers, they put them in a big vat, and they just extrude it out into the shape, and it is one molecule. So the reality is this number is usually some mind-bogglingly huge number. But if we're dealing with little teeny polymers, then we can start using this kind of notation. What I need you to know is that when you see this notation with a bracket, with the bonds sticking out of the bracket and a little number down here, a little subscript, I'll need you to know that that is, that's like shorthand for writing a polymer. You got it? Awesome. Also, addition polymerization, I need you to know. But if you know what an addition reaction is, you should know what an addition polymerization is, right? Is polymerization linking by an addition reaction. Moving on. The other kind of polymerization reaction we want to talk about is condensation. Now, can you possibly guess what molecule is made during a condensation reaction? Can you guess? Can you? Can you? Yeah, you can. You're going to make H2O in this one. You dig what I'm saying? So it's basically linking monomers by extracting a water molecule, and the leftover bonds that are just flapping around in space just link together, and there you go. You got yourself a polymer. So we are going to look at the process of, makes a monster molecule of polyether or polyester. Yeah, you can make ethers or you can make esters. Here's how you make an ether. I don't think we talked about this one yet. It's where you take two primary alcohols, you get them close to each other, and the two hydrogens and an oxygen break off and make H2O. And the leftovers, right, like this bond here flop around in space, and this oxygen bond flop around in space, make yourself an ether. To make a polyether, you just have each of these with a hydroxyl group on each side, and you throw them into a container, and then this hydroxyl group bumps into this hydroxyl group. These two in this oxygen break off, these bond across here, and so on and so forth, and you are left with this chain that's just like as big as you want it. And then you put it into a big spool, you weave those little things all together, and you make a little fiber. You take the fiber, you weave it into fabric, and there you go. You will have a polyether or a polyester. This down here is how we make a polyester, like, you know, the clothing and stuff like that. So what we do is we take we're going to take a molecule, a monomer that has an organic acid on one side and an alcohol on the other. Because remember, esters are an acid and an alcohol. Right? And so you put them in a beaker, you shake them up, and what happens is when the acid end bumps into the alcohol end, you get two hydrogens and one oxygen very close to each other. And that makes water. Because remember, anytime you take two hydrogens and an oxygen, you're going to make water because it's super duper stable and nature loves that. Right, so this oxygen then and this carbon are going to bond together. Right? And then the same thing happens on this end. You have an acid and you have an alcohol, and they will form this. Right? This alcohol and this acid form the next one, and then this one forms the next one, and this one forms the next one, and you make a fiber as long as you want, and you put it on a big spool, you weave it into a fabric, bam, there you go. And again, the notation for this, like the way that we would show it on a piece of paper that this is actually like a polymer, is we take our ester and we put it in these brackets with the bond kind of sticking outside, right? With the bond sticking outside and a little subscript indicating how many. Now, for us, we might make a really small polymer just to like you know, for like academic purposes. The real number here would be some astronomical number of like beyond human comprehension, but you know, there's how you make your polyesters, man. Do you ever figure that chemistry would be like how you make clothing? Well, can you believe it? That's it for today, guys. That's all I got. It only took 2 days for that to happen because, you know, Stu loves computers and technology. You lucked out. I'm not going to show up at your house with my overhead, although I almost did. But I do need you to do 2 homeworks, not 1, but 2. One is understanding organic reactions. This is the same kind as usual that has like reading in the beginning that will help you understand more. And then the second one here, organic reactions, that's your multiple choice one right from the Regents, standard practice questions. Gonna need both of them done from you. I hope you guys are having an awesome day. I'm gonna, and I'll see you guys around.